All right, guys, our last video ended on this slide here. We were talking about plate tectonics. We were talking about the movement of those plates, what happened at the different boundaries, subduction, rift valleys, volcanism, all of those different things. What we're going to focus on in this one is going to be specifically the rock cycle and also how those rocks are going to weather into soil and create the soil that we need for us to grow the crops we grow, the plants we grow to support the consumers in the environment, all of those things. So as soon as this program opens, we'll be able to get started here. Basically, the rock cycle is going to be a transition similar to like what the biogeochemical cycles were, where we can go, kind of in that cyclic pattern, to and from different things. So it's going to be, it says here, you guys can read that, it's going to be the alteration, destruction, and formation of different types of rocks. It's the slowest of all the Earth's cycles. Again, this one happens on geologic time. And geologic time, we're talking about 200,000 years being a small amount of geologic time. So when we're talking about going from sediment and then compaction into sedimentary rock, that process may take a few 100,000 years, if not a few million years, in order for that sedimentary rock to form. So we're looking at a very, very, very slow process with it. All right, now there's going to be three main ways that rock will form, because we have three different types of rock. We have igneous, we have sedimentary, and we have metamorphic. If we have igneous, it's all about cooling down of the magma. So the magma is not just some fictitious being. It's not like water. It's a molten form of rock, and it's all the minerals, all the different components that are contained within it. As that magma cools, we have that big puddle of magma here. As that cools, it solidifies into the different types of rock that we have. Anytime you have magma cooling, it's going to be forming igneous rock. When we have sedimentary rock, that's going to be where we have a layer of sediment that forms either on land or in water. A lot of times it's in water because, again, all the dead stuff starts to sink down to the bottom, rock starts to weather, those little particles go down, and then there's a continual buildup of layers of that sediment. Each time we have a buildup of that layer of sediment, now we have more and more pressure pushing down. The more and more pressure we have pushing down, the more that original sediment starts to solidify, and when it solidifies, that's what forms that sedimentary rock. Sedimentary rock is the weakest of all the types of rocks. In a lot of cases with sandstone and other sedimentary rock, you can actually break them in your hand. So they're not real strong types of rock. Igneous, on the other hand, is a very strong type of rock because, again, that's that cooling of that magma. It really solidifies into like a crystal structure where it has lots of backbone and lots of strength to it. Now, if we take either of these two types of rock and expose them to really high temperatures and really high pressures, we can metamorphosize them into the third type of rock, metamorphic rock. Anytime you metamorphosize something or morph into a new thing, that's going to be altering the chemical structure of it into a new compound. And we can either take igneous rock or sedimentary rock, expose it to that high temperature where it melts again, or high pressure where it reorders the crystals, and the outcome of that is going to be metamorphic rock formation. So when we look at this rock cycle, we have our three types of rock here. Again, igneous, metamorphic, and sedimentary. And we'll put little check marks of different colors over top of them so that we can kind of trace the path as we go. So let's just start with sedimentary. How does it form? We have to have weathering and erosion that happens. Weathering and erosion is key to sedimentary rock because we have to have that sediment, that parent material, be part of that sediment, whether it's sand, whether it's gravel, whatever it is. So, the weathering part of it, we can have acid rain fall on it and dissolve the rock away. We could have freezing and thawing, chipping pieces of rock away, whatever the case is. After it's weathered down and broken down from its larger piece, so we have a gigantic piece of rock here. After we weather it, it breaks into several smaller pieces. And if it continues to weather, then we get even finer particles as we go. After it's weathered, it has to then be eroded. Erosion is different than weathering. Weathering is breaking it down. Erosion is the transport of it. So when we transport it to that new area, now it starts to build up and we have that layering of the sediment. As that sediment layers, now it's compressed and continually put more and more pressure onto it, continually compressed into a smaller and smaller volume, and eventually that's going to form into our sedimentary rock. The two main examples, and again, no examples of everything. College Board's always going to ask you for list and describe 2 examples of sedimentary rock. So you could have limestone or sandstone as your examples for sedimentary rock. Sandstone is just a compression of sand into a rock. Limestone is going to be that chemical weathering, dissolving away the calcium carbonate. That calcium carbonate builds up in the sediment. As that calcium carbonate gets exposed to greater and greater pressures, that's whenever it forms into the limestone. And again, we talked about the limestone back in the carbon cycle, because again, limestone's chemical formula is calcium carbonate. So as the backbones of fish, as the shells, as all of those things that contain carbonates fall into the water, they start sinking down to the bottom, get trapped into the sediment, compressed into calcium carbonate, which is the limestone. Again, this is a big part of the carbon cycle. Number 1 reservoir for carbon on the planet is sedimentary rock because of the calcium carbonate part of it. All right. As that sedimentary rock is exposed to heat and pressure, then it can be metamorphosized into metamorphic rock. And our 2 big examples of that, and you guys probably have these in your house somewhere, are marble and quartz. Marble and quartz have kind of like those little veins that kind of run through. Those are all the different minerals that are contained within it. So you can see in this picture, it's got kind of the grayish background, but there's those little mineral veins that kind of run through. They're really, really pretty to look at. So a lot of people use them in their house as their countertops. Granite's becoming more and more common to be used, but the original ones, whenever I was a kid, if you wanted a high-end finish to your house, you always used marble. Now people are moving more towards the granites and the quartzes as opposed to marble, because marble, is becoming more hard to find, and it's getting more expensive because of that. Again, we're talking geologic time frames for this to form. As we mine that marble out, it's eventually going to run out for us because we don't have the 200,000, 400,000 years to wait for new marble to form. And again, marble, quartz, the metamorphic rock, their exposure of heat and pressure, exposure of these other 2 types of rocks rather to the heat and pressure. All right, that's not all that has to happen. In order for us to be able to naturally use these types of rocks, they have to be uplifted to the surface. And that's with all 3 of them, because again, they are going to form deep underground because pressure and heat is needed depending on which type of rock you're looking at. So as that formation is happening, it's happening really deep underground. It's going to take hundreds of thousands of years for that rock to find its way up to the surface. Now, we do mine all 3 of these so that we can speed that process up. There's limestone quarries. There's several of those even in our local area here, because we do have a lot of the sedimentary rock from back when we were in those more tropic climates. We had a lot of sand, a lot of carbonate ions from the shells of the organisms that lived here millions and millions of years ago. Places that have marble and quartz, they're mining for those constantly. They're used for building materials. The granite and basalt, more so granite, they mine for that as well, for people for their countertops and for statues and things. So when we look at igneous rock, it's all about these other 2 types melting first. So the metamorphic can go down into the hotter section of the mantle. It can melt. Sedimentary rock can do the same. After it melts, now as it cools off, it's going to cool, and the crystallization of those minerals are going to happen, and we end up with that shinier igneous rock with the granite and basalt. Now, here's the key to igneous rock. There's 2 different types of it. There's going to be extrusive and intrusive. If it's inside the ground, meaning underground, it's going to be intrusive. Right? If it comes out, say that there's a volcano here, and that magma comes out of the volcano, and it flows down the hill as lava. As that lava cools, that's going to form extrusive igneous rock. So you can remember the extrusive igneous rock exited the surface, and it's outside. The intrusive is inside the surface. It's underground. So what I would do if I was you guys is I would make up a rock cycle part of your biogeochemical cycles flip chart. You can have sedimentary, You can have metamorphic, and you can have igneous, and then arrows going between them, showing that all of these rocks can change into each other based on what properties they're exposed to. You know, if it's melting because of high temperatures, then it's going to be changing into the igneous, into the metamorphic. If it's going to be cooling, then it's going to be into the igneous. If it's exposed to pressure, it's into the sedimentary. So you guys can go backwards in the video, or pause it right now, and you guys can draw up your rock cycle based on this. Another simple way, just Google rock cycle, and it will have a picture of it. But include that into your biogeochemical cycles flip chart. Even though it's not a biogeochemical cycle, it's still like a geochemical cycle. There's no living component to it. It's just that geologic cycle with it. So when we focus on just igneous rock, again, it's going to be formed from the magma coming to the surface or underneath the surface, cooling off. As it cools, that crystal structure forms. And again, there's two types, intrusive and extrusive. Again, this is underground cooling, or inside the surface, and this is above ground cooling, or exiting the surface, outside the surface. All right. Regardless of which type forms, it can then get weathered once it's at the surface, breaking that down into sediment. That sediment then compresses over time and forms the sedimentary rock. And again, the keys to this one, it's going to be the muds, the sands, and gravels, all kind of compressing because those sediment layers are going to keep on building on itself, putting more and more pressure onto it. As that pressure intensifies, it squeezes those particles in close enough that they become solidified in the rock. Now, the key to the sedimentary rock, again, that's what's going to provide us our fossil record, because as that stratification, as those layers are starting to form of that sediment, let's say we have a little leaf that falls into there. Again, not very good drawer, you guys know that by now. So this is my leaf. As that leaf falls in and it gets compressed underneath the layers of sediment, eventually that organic material is going to rot and decay away, but it doesn't rot until after it's already put its indentation into those sediment layers. As that indentation stays there, now we have all of that organic material rotted away, that indentation's left behind, and it leaves an imprint of those fossils. The trick to the fossil record is only 1% of all organisms ever on the planet have ever left behind a fossil. Right? We have well over that 1% that have had the ability to leave fossils, but we only have about 1% of intact fossils because that sedimentary rock breaks down very, very quickly, very easily. You know, whenever we're talking about carbonates, as those carbonates are exposed, let's say that it's limestone, as those carbonates are exposed to acids, they start to dissolve away. So then if this one was exposed to, say, sulfuric acid from rain near power plants, or nitric acid from automobile traffic, or you know, other types of acid precipitation or acids that end up into the environment, we could have this rock dissolve away and we lose that fossil. So again, only 1% of all organisms have ever left behind a fossil for our fossil record. But that 1% is vital for us to know how natural selection has occurred over the years, how evolution has occurred, all of those different things. It tells us about past diversity levels. We can tell when we had our mass extinctions, all of that from just those 1% of the organisms leaving their fossils behind. Okay, our last type again is metamorphic. And metamorphic, this is going to be where we convert either igneous or sedimentary rock into our third type. And again, it's all about extreme temperatures and extreme pressures. It's morphing and altering that chemical structure of the rock into the new type of rock. And again, the main use for metamorphic rock is going to be building materials, whether it's, you know, for pillars, for marble pillars, or for marble countertops, whatever that. We use that primarily for building materials with it. Okay. So that wraps up the rock cycle, fairly easy, fairly straightforward. There's an activity on Moodle that you guys should be doing that kind of walks you through it a little bit more, gives a little bit more depth to what the rock cycle is all about. After that rock is made, though, we can't have living things live on rock. You know, lichens can live on rocks, but for the most part, all of our life is dependent upon soil. So we need to change that rock, whether it's igneous, whether it's metamorphic, whether it's sedimentary. We need to change that rock into soil. And we do that through weathering. The weathering will release the minerals. Once those minerals are released, now we can start supporting life. As we support life, then death and decay happens. We add organic components to the minerals and we have soil formation. So not only do we need it to be weathered, but it also has to then be eroded and transported and collected other places. All right, going to be two different types of weathering, physical and chemical. Physical weathering is just simply going to be mechanical breakdown. You take a rock and say there's a small little crack in that rock. That crack fills up with water. And if you're living in Western Pennsylvania, it's supposed to be below freezing here this next couple weeks. So that little wee bit of water that forms in that crack starts to freeze. As it freezes, it expands. So that small crack then becomes a bigger crack. And eventually that bigger crack splits that rock into two places, or two pieces rather. Right there, once it's in two pieces, that's nothing more than physical weathering. As that process continually happens, we break it down into smaller and smaller pieces. We can also have winds doing that same thing. As the winds blow in, they bring little dust particles. As those dust particles bombard that rock, it's acting sort of like a sandblaster where it's going to etch and chip away those chunks of rock, breaking it down into smaller rock particles, and then eventually breaking it and releasing minerals from it. Now, chemical weathering is a little bit different. It's not a mechanical process anymore. We don't have flowing water happening with it. We don't have water freezing. We don't have roots growing into the cracks and expanding and causing that physical breakdown. Now it's all about chemical alteration. It takes it from being one chemical and changing it into another chemical. The primary means of this is through acids. And those acids can be either acid rain, I should say acid precipitation, not acid rain, but it could either be acid precipitation or it could be acids released from plants. And if you remember when we talked about succession, we said that lichens are one of the big plants that excrete acid from their roots. So the lichens will grow on top of rock, they'll excrete acid from their roots, that will break that rock down and chemically weather it, releasing mineral components from it. We can also simply have acid precipitation happening, where we have the rock that's outside, the droplets of rain that formed up in the atmosphere hit that rock, and little wee bubbles will form and dissolving of the rock will happen. And as that water flows over top of it, then those minerals will be eroded away and taken other places. The big way that we get our acid rain is through sulfur components and nitrogen components. So when we look at the sulfur, the big place that we get that from is burning coal. Sulfur dioxide is going to be released, and we're going to learn about this later on when we talk about pollution. But we're going to have sulfur dioxide first. As that goes up in the atmosphere, it's converted into sulfur trioxide. And some of you guys may remember this. I'm sorry, I'm using the wrong exponents here. Some of you guys may remember this from when we did our biogeochemical cycle flip charts. You have the sulfur dioxide first, getting converted into sulfur trioxide, and then eventually it reacts with the water to form into sulfuric acid from there. Right? That sulfuric acid is what's going to fall to the ground and causes our problems with acid precipitation. The other components that we have are the nitric oxides. They're going to be produced from inefficient burning of fossil fuels, mainly diesel fuels and gasoline. So the diesel fuel will be burnt, will release nitrogen oxides up into the atmosphere. Same thing, it will react with the water vapor in the sky, and it will create nitric acid. Both of those two acids, sulfuric and nitric, will both cause the chemical weathering. So it doesn't matter if it's physical weathering or chemical weathering. The goal of it is that, not the goal, but the outcome of it is that mineral components are going to be leached out and eroded away. So again, physical weathering, cracks in the rock start to either have roots grow through them and expand as the tree gets bigger or the plant gets bigger, putting pressure on the rock, cracking it in half, or you could have water freezing and thawing constantly, eventually cracking that rock some more. After it's weathered though, erosion needs to happen because we have to have the concentration of those mineral components. So we have the weathering that occurs, the flowing water or blowing wind starts to collect those minerals into a more concentrated form. As those mineral components start to concentrate, now we start to have the things necessary for life to exist. As that life exists, now we start to have, leaves fall off, branches fall off, all of those different things, and we add an organic component to the inorganic component of those minerals. Once we start adding that organic component in, now it's when we start having true soil. And our soil is going to have a bunch of different functions. Do you guys remember when we talked about ecosystem services and things? The ecosystem services that the soil provides are the following. Again, it gives us the ability to grow plants because we need someplace suitable for those roots to grow and gain the nutrients they need. It's going to help to filter water. As the water goes through the soil particles, the impurities kind of get left behind, and it's just the water that ends up flowing through. By the time it flows through that soil, it builds up underground as clean. We don't want to say fresh, because fresh water is simply without salt. It ends up as clean water after it flows through the soil. All the impurities get left behind, and it acts as a natural filter for us. Think about it like an enormously large Brita. It's also going to give habitat for living organisms. We're going to have the worms and the grubs and mice and voles and all those little critters that live in the ground have a place to survive now. And again, a filter for pollutants, same basic thing as filtering the water. All of those pollutants get left behind and trapped within the soil particles as the water flows through it. So again, our ecosystem services, we have provisioning services, regulating services, cultural, supporting. When we look at these different services provided for us, we have to see where they're going to fit in, whether they're provisioning services, whether they're providing us something, whether they're support services, where they're going to help us out with other functions and all that stuff. So if we look, again, provisioning, we're going to get products obtained from them. That's going to be our fresh water. That's going to be our provisioning service. Our plant life that we have growing, that's going to be our provisioning service. All those different things that we have are primarily provisioning when we talk about the soil. Okay, now when we look at how the soil is formed, again, we said it was the breakdown of rock through weathering first. So if we have a place that's primarily rock and gravel, that's going to be immature soil. This is the youngest of the soil. So if you're asked a question on the AP exam where they give you these 3, 4, or 5 pictures, whichever one has the most amount of rock, that's going to be the oldest, the youngest of the soils. Whichever one has the most organic components, that's going to be the oldest of the soils. Sorry about the announcement, but as time goes on, again, more weathering is going to happen. More weathering means more minerals are added up into that layer. The more minerals there are, the more organisms that can live. The more organisms living, there's also going to be more death. More death happening adds more organic material, and as we gain more and more organic material, we start supporting those larger plants. Remember, that's the reason why primary succession took so much longer than secondary succession, because we didn't have to form the soil in secondary succession. All right, so when we're forming the soil, we're going to have our parent material first. Parent material is nothing more than rock. So we have the rock that undergoes physical and chemical weathering. All right, that rock, it's going to weather at different rates based on different things. It could be the climate. If we have areas with more rain, it will be quicker to weather, because the more rain you have exposed to the rock, the more flowing water you have going over it, the more etching of the rock you have happen. The windier the areas, the quicker this parent material is going to break down. And it also, the colder it gets, you're going to have that freezing and thawing, which is going to help out also. Topography is going to affect it also, because again, the different topography has different conditions where it lives at. Sorry, you guys know that annoys me when we get 9 million announcements during a period. And then organisms are another big one. The organisms, as they go through the different layers of the rock, they're going to be interacting with it. They're going to be eating different things, pooping as they go, peeing as they go. That's all going to add organic material into it. So that conversion of the parent material into soil is going to be quicker in those areas. When we look at the climate part, once we have that life established, then the warmer and the wetter it is, the faster the soil forms. Now, when we're looking at the parent material and breaking it apart through physical weathering, being cold actually helps us out because we have that freeze thaw that helps to expand those cracks and break them down into smaller pieces. But once we have life established, the warmer and wetter it is, the faster the soil forms, because now we have more life formation and quicker decomposition. That's how the topography affects it too. The higher in altitude you go, the colder it gets, the slower the soil formation is. So on a mountain, you have faster soil formation down towards the bottom, slower soil formation up towards the top. All right, we're going to stop there for this one and talk about the horizons in the next video, because I want to just cover those in one big video, because this is going to be an important part of soil.